Today I'm going to present the paper process explanation. It's a joint work with Avram from TTIC and Steve from Purdue and great Chirag from Stanford. So as we all know, so should I do anything about this now? Okay. So as we all know, machine learning systems and frameworks are being used in many different domains and aspects of our life for making decisions. And we rely on them to give us right predictions on what we do and what we shouldn't do. And the problem is, there are many times that these systems are very complex and the decision that they make itself could be correct, but that's not enough for us because it's in a very high risk domain. And what we want is for them to prove to us or explain to us why the prediction they're making is being made. And so we want them to give us some sort of explanation. One of those aspects could be a medical scenario that you are a patient and you go to the doctor, and your doctor talks to all of these AI models. And these AI models are, of course, very complex and they know many things about many things. And this doctor gives the AI model all the information it has on you and asks it, what should I do? And the AI model says that this guy needs surgery. And doing the surgery is a very high risk situation. So you want to know why because you're so scared. And you ask your doctor, why do you think that? And the doctor doesn't know what to tell you because it's asking this AI model, and doctor doesn't know why the AI model is saying what it says. So the doctor goes back to the robot and it says, why do you think this person needs a surgery? And the AI, one of the explanations that it could give the doctor and is kind of satisfying is that, well, this patient is kind of similar to this guy I've seen before, guy X, and in terms of, I don't know, age and the symptoms that he has and all that. And patient number X has done the surgery and he was successful and he benefited from it. And it's not just patient number X, there was patient number Y that also had kind of a similar situation, and even him benefited from the surgery. And he gives you all the list of those things, of everything he's seen before and why he's making that decision. And doctor tells you all about it, and then you're happy about this decision. Does it make sense? Okay, so this is the vague hand wavy intuition of what we want the explanations to be. And in order to understand that, we try to model it as a theoretical machine learning framework. So we go back to all the definitions we have in machine learning theory. So to be concrete, imagine you start with a data set S that has endpoints in it, meaning that you have a classification problem. You start with point x1, labeled as y1, xn, yn, and so on. And then you imagine there's a ground truth way of making decisions about this procedure that you're facing that is H star, means that for any point that you get, there exists a labeling that is with respect to H star that is perfect. This is the right way to label things. And then you imagine this H star is coming from a class of hypothesis H. And then you imagine this data set that you have is also labeled by this H. So it's realizable by the H star target function that you have. And then this patient, this guy, this test point comes and you want to label this as positive, but then you want to certify why you think this point is a positive. So that's the concrete way of modeling what we're trying to capture. Is it clear so far? All right, so if you want to do that, not only we want the prediction on X to be correct, we also want to be able to certify it. And for that, we use this notion of agreeable region, which is central to all of the analysis that we do. So imagine you think the right label for point X is a positive label, and we say that this point X labeled as positive lies in the positive agreement region of H with respect to the data set I have so far, meaning that every hypothesis that I have that comes from hypothesis class H and is consistent with data set I have so far must label this point as positive. If that's the case, this data set I have is a certificate for my point because there's no other way for any H in this hypothesis class to label it otherwise, right? So in this case, you would say, okay, if you have such a data set S and X and its label lies in the agreement region of that, S itself is my certificate. And then the question becomes, if this set is actually a big set, can you extract a subset of this S as a star such that it would still have X labeled as is, meaning positive, in its agreement region, or equivalently, it means that S star would be a certificate for X. So that's the question we're going to answer. Is it clear so far? All right.
Sorry, one question. What do you mean by consistent?
So it means that the hypothesis does not make any error on it. So it's going to be realized.
Okay, so 100% accuracy.
Yes.
All right.
Any other questions? All right. So what we covered so far is that you start with this data set. If this data set is labeled with some edge star and it got a label, the test point that you see as a positive. So that's the question that we're trying to answer. Okay, so if you try to write down the motivating question is that suppose you're given a training set S and you're given then a test point X, and this test point is in the agreement region of your data set. The question becomes, what is the smallest size certificate S prime that I can extract from this data set that would guarantee X should be labeled as I did it, right? And visually to model it. So suppose this is your training set, and the agreement region of S if could be the set S itself or like a superset of it. And then I get a test point X, and I want to understand if there exists a subset of S prime that would still have X and Y in its agreement region. That's everything we've discussed so far. And to understand that a little bit better, we start by understanding the class of half spaces. So suppose we are in d-dimensional space. So the space that we are working with is RD. And imagine the hypothesis class that we have is the class of homogeneous half spaces, meaning that they're going through origin. And this bunch of data that I have, some positives, some negatives are given to me. And I search in my hypothesis class for all the hypotheses that are consistent with this. This is one of the boundary hypotheses. Like if it goes tilt a little bit to the left, it's not going to realize the data anymore. So it's boundary thing. And this one is also a boundary hypothesis. So if it tilts a little bit to the right, it's not going to be consistent with data anymore. And the positive agreement region would be this part that is colored as blue. And it means that if I have any test point X here, I should be able to get a certified, right? But since this class of hypothesis that I have is homogeneous and goes through the space, I wonder if I label my positive points as S plus and negate my negative points as minus and put them there, like I'm mirroring them because the hypothesis class is going through origin. And then take the union of them, meaning if I get S plus and S minus and get the union of them, the cone of the union of them has X in it and is also the agreement region that I was looking for. Does it make sense? So the cone that I get from this data set is exactly the agreement region, right? And I wonder if I can extract a subset of S plus and S minus that is smaller than this set and would still have X in its agreement region. And what's cool about it is that there's Gary-Theodori theorem that tells you that there indeed exists a set S prime that is a subset of this set and has size at most D and would have X in its cone, meaning that X is in the agreement region of that, meaning that S prime is my certificate, right? So in this case, I was able to get a certificate of size at most D, which is just this point and that point, like this and this. And then I wondered like what's going on. Is there any questions? No questions? All right. So if you look at it, the certificate size now is bounded by number D. And what is cool about number D is that it's also the VC dimension. So we wonder, is it related or not? And we want to show that it's not. So we move to another hypothesis class. And the second class that we look for is the class of singletons. So suppose you're in a finite domain of endpoints. And the class of singletons is a class that spikes in just one of these points. So for example, H1 just labels X1 as 1 and everything else is 0 and so on. So Hn labels Xn as 1, everything else is 0. And suppose that I'm given this training set S that has the first n minus 1 points in it, and everything in it is labeled as 0. So this is consistent with Hn, and indeed has Xn and 1 in its agreement region. Does it make sense? So I know if I have a set of size n minus 1 and everything is labeled as 0, the nth point gotta be a positive point, right? Because it's a class of singletons. So the certificate in this case has a size n minus 1. And then I wonder, the VC dimension of singletons is 1. So can I get a certificate that is actually just size 1 or less than this? And it turns out no, because if you leave out any point from S, then then your nth point would not be in the agreement region anymore. So it shows you that the VC dimension probably has nothing to do with my certificate size. And then we wonder what has something to do with the certificate size. Right, do you have any questions? Is it clear? All right. So we go back to the motivating question, and we understood for half spaces, this quantity that we looked for was D, and for singletons, it was n minus 1, and being the size of domain. And we realized that it's related to a quantity called a hollow star number, which I'm going to define in the next slide. Do you have any questions? Because I'm moving too fast, I don't know. All right. Okay. So I define the hollow star number. So suppose you have a hypothesis class H and you're given a set S. We say the set S is a hollow star for this hypothesis class if S itself is not realizable by H, meaning there is no hypothesis in hypothesis class H that would label S in a way that it is, right? But if I take any points out of this set, it's going to be realizable by H. It doesn't matter which one, any of them, if I take them out, it's going to be realizable by H. And I call this set S my hollow star set for this hypothesis class H. Right? Is it clear? For example, if you have a class of singletons and you have it on endpoints, and imagine you label all of its endpoints as 0. So this set, like if you have x1, 0, x2, 0, xn, 0, this set, there's no way for it to be realizable by the class of singletons because you got to spike somewhere, right? But if you take any point out of this set, it's going to be realizable by H immediately, right? So this set of x1 to xn, all labeled as 0, is a hollow star for the class of singleton and has size n. Right? Is it clear? Okay. So that's the definition of a hollow star set. Go on. Hi.
So, so when you say hollow star number, you're just saying the size of the set?
So there exist different kinds of set who would satisfy this property, and a hollow star number would be the size of the largest such set. So the hollow star set's size is upper bounded by the hollow star number. If that makes sense. So the size of largest hollow star is my hollow star number, and this is the definition of a hollow star set itself.
Okay, thank you.
You're welcome. Any other questions? No questions. All right. So what do? We defined hollow star and we defined hollow star number, and we want to say it has something to do with the certificate size. That's what we're going to do next. And okay, why is it here? Okay, so we want to talk about the minimum certificate size, and we want to say that the minimum certificate size is exactly the hollow star number. So suppose you have a test point, and imagine that this test point lies in the agreement region of a training set that you have. And your training set is, of course, realizable by H, right? And we say that the size of a certificate for this test point is going to be exactly hollow star number minus 1. This is the first claim that we're going to make. Is the theorem statement clear? All right. So what are we going to show is that first, we can always find a certificate of size at most n minus 1. And then we're going to show that there exists instances where the smaller certificate is not possible. right? So we started with a training set, and this training set is realizable by the hypothesis class that we're talking about. And then we got a test point. We're assuming that this test point lies in the agreement region of the training set we have so far. And then we wonder what is the minimum certificate size for this test point. And we're saying that there exist instances that the size of the certificate is going to be lower bounded by the hollow star number, and it's also upper bounded by the hollow star number. So it's going to be exactly hollow star number, right? Right. I'm going to let it sit for a while. I feel like I'm talking.
I think it's clear. Yeah.
Okay.
Thanks.
Okay. And we also show all of this hold if you have B number of corruptions in your data set, and then we define B robust hollow star number and so on about it. So to show an upper bound, we say that we can always find a certificate of size at most n minus 1, right? So suppose X and Y lies in the agreement region of your data set. For example, you have the class of singletons, you have n minus 1 points, and you take the last point, and it's in the agreement region of your data set. And consider the smallest S prime in S such that it would be in the agreement region. Like this is the smallest such set that we can consider. And the claim is S prime unioned with this point that I have and its label flipped is actually a hollow star, right? And this would mean the size of S prime is going to be upper bounded by n minus 1. So I should show why this is a hollow star, right? So for that, I should show that this set is actually not realizable by edge, which we did already because like it'll be the singleton of everything 0. And then I should show that if S prime is realizable, and we also know that S prime is realizable by edge because S is realizable by edge. So if I take the test point with the flip label out, which is one of the points out, it's going to be realizable. So it satisfied one part of the hollow star definition. And if I put the test point back in with the flip label and take any point out from S prime, it's also going to be realizable by edge. And the reason is we started with this assumption that S prime is the smallest certificate. So if I take any of those points out, it's not going to be a certificate anymore. So there's got to be the case that this S prime with 1 point out union with X and its label flipped should be realizable by edge. Does it make sense? So we showed that S prime union with X and its flip label is indeed a hollow star. And we know that the hollow star set size is upper bounded by hollow star number. So that's our upper bound. Right? Is it clear? And then we should show the lower bound of it. And okay, so for the lower bound, suppose this data set that you start with, S, it is itself the largest hollow star. No, imagine you start with S and it's the largest hollow star that you have. And I want to show that this set is, if you exclude the last point, it's gonna the set that you get from it is gonna be a certificate for the last point with the label flipped. Is that clear? So I start with the largest hollow star that I have. So this set is not realizable by edge, right? And I take the last point out and I said, this is gonna be a certificate for the last point with its label flipped, right? So this is, suppose this is the S. This is the S. And I'm saying that this green things is a certificate for this last thing, right? And then I have to show that there exists no set that is smaller than this as that I started with. That would be a certificate for my point. And that would follow from the definition of hollow star because I know that if I exclude any of these items, it's going to be realizable. So if I start with a training set that is a really, really bad training set, it's the largest hollow star that I have, it kind of forces me to have the certificate size be lower bounded by hollow star number -1. That's our lower bound. Is there any questions? Okay. So this was all worst case scenarios. So you don't have any distributions, you just have combinatorial stuff going on. And then we wonder what happens if our data set and test point is coming from a distribution. Would it be any better? So suppose we want to certify a point X and it's labeled H star of X. And we have a training set S that comes from a distribution. The first thing that we would need is for this test point to actually lie in the agreement region of the training set that we're drawing from the distribution D, right? And the question is, how large of a training set should we draw for that to even be satisfied? That's the first question. So imagine we are in 2D and we have a uniform distribution on x1, x2, x3, and the hypothesis class that we work with is linear separators. And we want to say that we want to certify a prediction that we do on point X that is like on the middle of these things. And the way that the certificate that we would need to know that x1 is labeled as positive, x2 is labeled as positive, and x3 is labeled as positive. So if we draw from this distribution, we have to see all of these 3 points, right? And we need to see all the labels of all of them to know that the x is going to be a positive point. And for that, we're going to define a notion that is distribution dependent. Is there any questions? Okay. So we say that H star is the target hypothesis that we're looking for. The distribution that we are getting our points from is D. And from all the hypotheses that I have in my hypothesis class, get a subset of this hypothesis such that this subset would disagree with H star on point X. So I define H of X as a set of all hypotheses that would disagree with H star on labeling X. Okay? And then I would define the certificate coefficient of X with respect to this hypothesis class and H star and the distribution as what is the most malicious H that I can get, meaning that imagine you draw your data set you draw this data from your distribution D, and of all the hypotheses that disagree with H star, what is the minimum probability mass this different hypotheses could get wrong with respect to this distribution? And the smaller this number is, the harder it is to identify the worst hypothesis in this H of X. Is it clear? So go on.
Yep. Like I had a quick query. Here you have assumed that your distribution is uniform and marginal. Uh, like, can we have different sort of assumptions here with respect to the distributions?
It's
Yeah.
not dependent on distribution, so that was just an example, but
Okay.
all the quantities that we define are for any distribution, for anything, for any hypothesis class and so forth. These are just like toy examples to make it concrete.
Cool.
Okay. All right. So we define the certificate coefficient as this quantity, and we try to understand what is the certificate coefficient for this example of uniform things that we have. So in this class, any point that would get X labeled differently from H star would at least disagree with one of X1s and X2 and X3. And that's the best they can do, like the most malicious thing that they can do. So your certificate coefficient is actually 1/3. And we're trying to beat that. That's our goal. So we're gonna draw a sample that is so large that it's gonna avoid this very bad hypothesis to fool us. That's our goal from so far. Questions? No questions? So what we say is that for any hypothesis class H with BC dimension D and a marginal distribution D, and this target hypothesis that we have for any test point that has certificate coefficient epsilon X, we would need exactly this theta, like this number of samples to know with probability 1 minus delta. This is in our agreement region, like X is gonna be in our agreement region. And once it is in our agreement region, the data set that we draw is itself our certificate. So that's what we're gonna show. And we also show if you have some data that is corrupted, we're going to get an additive term of B being the number of corrupted points the adversary has injected into your data set. And this is what we're going to show. Is it theorem statement clear? All right. Okay, so we show the upper bound for when edge is finite. So imagine, like, consider this class that we define edge x, which is all the hypotheses that would disagree on x with edge star. And we define epsilon x with respect to such class. And then we fix any edge from this class. So we fix any edge that would disagree with edge star on x. And we would say that, well, for this hypothesis, to make an error on the data set that we have drawn, if the data set size is m, the error is bounded by this number. And then we take the union bound over the size of h of x, which is bounded by h, and we say, okay, so this many samples would suffice for us to say that x will be in our agreement region. So we're essentially trying to make sure that any hypothesis that we learn from our ERM has error bounded by epsilon x. That's what we're trying to do, and it's exactly like pack learning in that sense. Okay. And okay, if the hypothesis class that you start with has infinite cardinality and has like finite VC dimension, you can do the same thing that you do in learning theory and get a bound that is dependent on VC dimension. That's what we show. And then that's the distributional case. So once we've done that, we have this data set that we've drawn as our certificate. Is there any questions so far? No questions. Great. But we wonder if you're in this distributional setting, is the certificate size that we have, which is essentially our sample size, an optimal thing or not? And we show that it's not. Why? Imagine that, so this is the sample complexity that we got, right? And it's dependent on epsilon x, it's dependent on d. If you have corruption, it's also dependent on b. And imagine that the distribution you start with is a uniform distribution on a unit ball in the dimension, and the hypothesis class that you have is again linear separator, and it labels everything in this ball as positive, but you get a positive point, and you get a test point, and the test point that you get has coordinates half 0, 0, 0, 0, 0, 0, and for this specific x, the epsilon x that you get is exponentially small in dimension, right? So here, your epsilon x is really, really small. So the number of samples you have to draw is 2 to the power of d, right? And if you look at it a little bit longer, we understand that we reweight this distribution so that this x becomes the center of the distribution, like in a smaller unit ball, then our epsilon x would actually be half, because any hypothesis that would get x wrong would get half of your distribution wrong, right? So if I take points from d and reject them 2 to the power of d times, I can reweight d to get dw, and in that dw, my epsilon x goes from something exponentially small to something constant, meaning that it's very, very easier for me to certify it. And if that happens, then I would need just d samples to certify x, because here epsilon x becomes a constant, and the only term that I care about is d. So if I do this reweighting, my certificate size is going to be d instead of d to the power of 2 to the d, right? And the question is, if I have a reweighting procedure that is polynomial in 1 over epsilon x dimension, and the mistake budget, can I get a certificate that is just better? And can I do that without knowing the distribution that I started with? And that is the open question that we don't know. Yeah. Is it clear?
Yeah, so like this halves from D to DW, the region kind of halves when you kind of have the ball of radius 1 by 2 here. Like, could you
I'm
explain this
sorry.
again?
I don't think I understood the question.
I was saying just with respect to, could you explain this again with respect to the DW that you got from D here?
Okay, so you have a uniform distribution that is D. So every point that you get is going to be in the first ball, the
Hmm.
lighter ball. And then I say, if that's the distribution you're working with, and the test point that you get is x, which is coordinate half 0, 0, 0, 0, 0, the epsilon x for this point with respect to this distribution and this hypothesis class is going to be 2 to the power to the d, 2 to the, like that number. It's exponentially small, right? And this is bad for me because if I want to certify this, I'm going to have a sample size that is large, really large. It's exponentially in D large. But there's something fishy about it. What is fishy about it is that there exists a distribution that if I have that distribution instead of the distribution I started with, I'm gonna be able to get a certificate for this point that is really small. For example, if I have D points that are just around this, it would have X in its convex hull. So that would be the smallest certificate I can get. And I'm like, wait a minute, that is dependent on my distribution. So if I have a procedure that would reweight my distribution, meaning that I would reject sample from the D I started with in a polynomial in 3 quantities, the budget for poisoning that I have that I'm not showing here, the BC dimension D that I'm showing here, and 1 over epsilon x, can I get something that is better and would give me a certificate size that is like more optimal? And in here, we show that that happens because from every 2 to 3 samples I get, one of them is going to fall into dw, and it's actually polynomial in d, b, and 1 over epsilon x. And the reason is epsilon x itself is the exponential into the d. So that is happening. And we wonder if you don't know d, can you come up with an algorithmic way of reweighting the distribution that you don't know so that you can get a certificate that is optimal in size? And we don't know that.
Thanks.
You're welcome.
Can I also ask a question?
Sure.
Are there any restrictions on how you can reweigh D? Does it mean you have to stay in the support of D?
Yeah,
Or-
you definitely stay in the support of D because you reject sample from it, but you also don't want to draw many, many, many exponential samples and say that I can just keep whatever I want. So you want it to be polynomial in these 3 quantities that I say, BC dimension, poisoning budget, and 1 over epsilon x.
So it's,
And then,
yeah, so you're
and
allowed to do any rejection sampling.
yes. And to do that rejection sampling and be useful, you have to know D, and we wonder if we don't know D, is there an algorithmic procedure that would give us like the small certificate that we could have gotten if we had a better distribution, and we don't know that. Is it clear? Okay,
Yeah, thanks.
welcome. Okay, so that is the last thing I wanted to talk about, and then we do the summary. So we introduced the notion of certificate for tests and predictions in terms of subsets of training data. And we did the worst case analysis when you don't have a distribution and everything in the combinatorial world is really, really bad. And we understood that it's connected to some property called a hollow star number of a hypothesis class. And we show that tight sample complexity for the training set when you have a distribution and when you don't have a distribution. And we also show that if you have a distribution, it's going to be connected to something called certificate coefficient epsilon x that we discussed. And we also show, we didn't talk about it, but in paper, we show the robust version of this, meaning that if you have points that are poison in your data set, all of these definitions would be robust this, be robust that, and then we show bounds for that too. And then we also pose some open questions about the distribution and stuff. Yeah, that's my talk.